From this lecture, we expect students to come away with 3 learning outcomes. Firstly, to be reminded of, become familiar with, once again, object orientation concepts. The second learning outcome is to sort of become familiar with, or at least understand the rationale behind OO design. That is, why do we do object-oriented design? And then thirdly, which is the most important learning outcome, is to become competent with one technique for object-oriented design, which is pretty much a best practice nowadays, known as responsibility-driven design. Object-oriented design, or OOD, is considered a best practice in design. Most new applications developed are object-oriented apps, including, believe it or not, COBOL applications, and either explicitly or implicitly, an object-oriented design process has been followed in their development. So what is OO design? It's essentially a technique that reflects the real world in your program. Why is OOD good? To begin with, it is built around the notion of abstraction, which is the separation of the interface of the entities in your program from their implementation. This helps in more easily understanding the component, or the entity being developed, and also allows the implementation of the component or entity to vary while keeping the interface the same. So basically, the calling program or the programs that use these components don't have to change even as these components evolve. OOD also brings in a more holistic model of abstraction that encapsulates state, the variables in a program, information, as well as behavior, essentially methods, into a class. This kind of holistic model of abstraction is more reusable than a procedural approach which only encapsulates behavior. Programs represent domain concepts, or rather application domain concepts. So the entities in the program correspond to these concepts. Anecdotal or empirical observation has shown that if the abstractions in your program mirror the real world, components were designed and evolved in a manner that people could relate to. Also, the real world has useful concepts that were brought into programming languages. For example, polymorphism. A table is a wooden object. A table is also a place to eat. Essentially, an object playing different roles within its domain. This notion of polymorphism actually came from the AI folks that were seeking to represent the real world. And if you think about it, polymorphism in programming languages is implemented by what is known as inheritance and the concept of interfaces. The second concept that was brought in from the real world was the notion of collaboration, which is that objects in the real world achieve goals by collaborating with each other. The key design principles within OO design are the following. The first is loose coupling, which is that the using entity knows as little as possible about the used component. This allows for change in the used component. This is typically enforced by what is known as the information hiding capabilities of the encapsulation model. By encapsulation model, I mean things like classes, interfaces, modules, things like that. Okay? The next key design principle is one known as cohesion. High cohesion allows for easier reuse because the scope of reuse is well defined and hence more understandable. So what is cohesion? Essentially the fact that an object implements one well-defined thing. The third key design principle is responsibility-driven design. This is essentially an OO design technique. This technique is scenario-driven. Hopefully you remember scenario-driven from your earlier lecture on incremental and iterative development. And it's a technique by which an object-oriented design is captured on what are known as CRC cards, or Class Responsibility Collaborator cards. Let us now do a terminology check about object-oriented concepts. The first concept is the concept of a class. A class is the state and behavior implementation of an object. In some languages, such as C++, a class is also a specification of the interface. The type of an object is the specification of the interface. That is, how would you interact with this object? An object is an instance of a class. It is the actual manifestation of a class. A method or function is an operation or a specification of a single behavioral element of a class. So a class has multiple behaviors. Each behavior is implemented by a method, and a method or function is one of those. A class method is a method associated with the class. An object is not needed in order to invoke a class method. A subclass, which is an extension of an implementation, is a class where the implementation of the class is inherited from a superclass, and the subclass could then extend it. A subtype, which is an extension of the interface, inherits an interface and could extend that interface. An interface is a specification of what is sometimes called the behavioral contract that the object has to meet. So this is the way somebody interacts with an object, and it's the way the object then returns back values or interacts with the object that is trying to collaborate with it. An abstract class is a class that is not instantiated. Essentially, an abstract class is meant to be only an element of reuse. It has to be subclassed before objects of it can be created. Finally, a virtual method is a method that might or might not have an implementation, that will not have an implementation, and it's a method that has to be implemented by a subclass. So what is the goal of object-oriented design? Obviously, it is to design your program, but specifically, the goal of OO design is to identify classes and responsibilities that will collaborate to meet the functionality of the system. Object-oriented design takes place using 4 steps. The first step is to identify the classes in your program. The second step is to identify and allocate responsibilities to your classes. The third step is evaluate this allocation using an object-oriented checklist. And finally, the fourth step is to validate this design, this allocation of responsibilities to classes using what are called scenario walkthroughs. So the first step is to identify objects and classes. How do you do this? Well, you begin with any work products that you have prior to your design. Requirements work products such as the storyboard, analysis work products such as domain, problem, and solution analysis, additional requirements work products such as use cases, any notes you might have on the system, anything that you have. And then you examine these work products for nouns and noun phrases in these documents. These nouns and noun phrases become candidate classes. Next, you examine the adjectives as candidate attributes. So for example, the word red in red car is likely to be an attribute within car. The attribute is likely to be called color. You also use adjectives to identify subtypes. For example, you might see a adjective such as sports car. Yeah, it's probably a noun phrase, but in any case, sports is qualifying the car. Yeah, and that might mean that you have a superclass called car, and then you have a subclass called sports car. You try to group these nouns into categories. These categories could potentially become abstract classes or superclasses. You write down briefly the purpose of each class. What is this class supposed to do? Okay, and use this description of each class's purpose to eliminate redundant classes, consolidate classes, things like that. By the way, note that the same technique could be used for analysis, and that's actually called object-oriented analysis. Except typically you would draw the nouns from the problem domain, okay, not so much from requirements, but from other documents that describe the domain. And here you're not trying to design a system. You're seeking to understand. You're trying to understand an existing system. Your next step is to identify and then assign responsibilities. To do this, you start with the verbs and verb phrases, that is your actions, in all the notes and documents that you have collected so far. These become candidate responsibilities. Then you do the same step where you try to define each verb or verb phrase. You do your consolidation, and then you try to assign these verbs and verb phrases to the appropriate classes. Okay? You try to distribute these verbs and verb phrases appropriately, evenly, so that you don't have one humongous class and many small ones. You check that adding a responsibility to a particular class doesn't kind of break the class definition. So for example, if you had a responsibility called finding directions, it probably wouldn't belong with an ATM or ATM class. You try to locate the responsibility with the information that responsibility might use. Yeah. And you also try to locate related responsibilities together. Okay. The question is, which rule prevents you from creating one humongous class? Certainly 3 and 4 might lead you to create one class with everything in just that one class. It is actually rule 1 a little bit, and then certainly 2. By the way, note that rules 1 and 2 force cohesion and kind of act against 3 and 4. Now that you've identified responsibilities and classes and you've done the allocation of responsibilities to classes, you should now do a validation step. Okay? Basically, you evaluate your assignment of responsibilities to classes using a simple 4-step checklist. Basically, you examine each class and see if it has a clear and simple name that is specific and not general. Okay, so a name like manager would be too general. A name like resource manager might mean the class is correctly defined. The second thing is, when you look at the description of the class, is it a cohesive, clear description of its responsibility? If you find that the definition of the class has many conjunctions, ands and ors, things like that, then this class is probably not an appropriate class. The third thing, and this is really this is the most important rule in this checklist, is that the class must have long-lived state. Essentially, this rule prevents what are called procedural classes from being created. Procedural classes are those classes that only implement actions. They don't manage any state or maintain any long-lived state. And then the fourth checklist is a class should not be created in isolation. It should have collaborators. The next step is to identify the collaborations among these classes. That is, how do these classes work together? Which classes do these classes that you've identified work with in order to implement the functionality of the system? Yeah? So in order to do that, what you do is you examine your requirements, your use cases, you create these simple scenarios, and then you take your scenarios and you walk through the scenarios with your classes so that you begin to understand, as each step in your scenario takes place, which class is handling that step or that responsibility. This will help you identify the interactions between classes, and these are the collaborations between classes, and this helps you identify the collaborators among those classes. And then as you do all this designing, identifying classes and responsibilities and collaborators and so on, you record your designs as you go on on these CRC cards. Essentially, CRC cards are 4x6 or 3x5 inch cards, and they give you an active technique. That is a technique in which all the members of your team are interacting with each other for recording, refining, and documenting the design. In addition to a means of recording the design, it's a means of socializing the design so that your entire team understands the design and starts to own the entire design. And here are more examples of CRC cards. So now this slide tries to illustrate what is gained by applying the object-oriented checklist, the design checklist, the 4-step design checklist that we presented in a previous slide. Okay. So, most of you would have taken CST 560. Essentially, for those who haven't, it's a course in which students design and develop a emulator, a linker, loader, assembler, and so on. Yeah, just looking at the emulator part of the project, the classes that typically students come up with are classes like the main class, the loader class, the machine class, the memory class, the register class, the instruction class, and the word class. Okay? Now, when the design checklist is applied to these classes, you will find that the main class and the loader class don't really maintain long-lived state. The machine, memory, register, instruction, word, they're all maintaining state. The machine is maintaining the state of the machine, the state of actually the memory. The memory is managing all the memory elements in the machine, things like that. But main and loader simply are operations. Main kicks the whole thing off, and loader loads the program from a file into the computer, and that's it. It doesn't do anything and goes away after that. Okay? When the design checklist is applied, what happens is that the classes get configured in the following way. You get a machine class, a storage class that contains both the memory and the registers. You get a word class and an instruction class. This consolidation essentially reduces, you will see that this consolidation reduces the coupling among classes. So for example, the loader class doesn't need to know the exact implementation of memory, which it would have to do in the previous design. Now the load operation is inside machine, memory is inside machine. The entire knowledge is kept inside the machine class. So now let's walk you through an example. And this example applies responsibility-driven design to designing a tic-tac-toe game. Okay, let's say this tic-tac-toe game is supposed to be implemented on a mobile device or whatever computer. Okay, so let's start by describing the game. Tic-tac-toe, or noughts and crosses, as I used to know it, is a pencil and paper game for two players. Players take turns marking spaces in a 3x3 grid, either with an X or an O. So one player marks the grid with X's, the other player marks the grid with O's. You're not allowed to override somebody what the other player has written. The player who succeeds in placing three marks in a horizontal, vertical, or diagonal row so that they're in a straight line wins the game. Okay. So now if you go through the description of tic-tac-toe and pull out nouns and verbs, here's what you get. So here are the nouns you might get: pencil, paper, game, knot, cross, player, XO, space, symbol, grid, so on. These nouns are candidate objects and candidate classes. What verbs might you find? Take turn, mark, goes, place, win, implement, play, playing first, display, accumulate. These are candidate responsibilities. So now let's do the consolidation. So the first thing, of course, is you got to understand what each object means. So you'd actually go through a definition step and write down all the definitions of all these different objects. Once you do that, you can then do the consolidation. So here are some consolidations you might do. You might remove pencil and paper from the list of candidate classes as physical things and not relevant to a computer-based game. You might observe that symbol and mark are identical and decide to retain symbol. Could retain mark as well. Observe that not and O and cross and X are identical, so remove one of them. User and player seem to have the same definition, so what do you do about this? Retain player as the player in the game while noting that the user is the human playing the game. You might find that human user and human might be identical concepts, or maybe further that these two as well as computer are instances or subclasses of player. We don't know. But just keep that in mind. Realize that board and grid are close enough in meaning that one of them could be removed. Decide to keep grid and in fact make it more specific by calling it game grid. Now you figure out what to do about screen. Since it appears to be a physical component of the computer, a first inclination might be to remove it, but then you think, wait a minute, something has to handle the board or the visual display of the board. So either we have the board class and then handling both the representation of the board and the display, or we could separate the data structure that represents the board from its visual manifestation. So in fact, what you do is maybe rename board decide to retain screen, and since we now have board available because we renamed, we consolidated board and grid to be grid, decide to rename screen board. Consider row as a component of game grid, and vertical row and diagonal row and horizontal row as essentially being different subclasses or instances of row. Don't quite know which ones yet. Consider session as being an instance of a game with score being either an attribute of the game or potentially of one of the two players. And now you do a similar consolidation with the verbs. You see take turn, goes, and play. Just retain play. Realize that mark and play seem to mean the same thing, and so you decide to keep place, and in fact refine it further by calling it place symbol. You remove implement because that's something that applies to the whole game. That's what you're going to do. So it's not relevant to the game itself. So you remove it, and then you retain display, accumulate, exit, and reset as responsibilities. And so now we are left with the consolidated set of classes and responsibilities. You have, for classes, you have symbol, player, human, computer, board, row, and game game has the attribute score. You might have objects or instances that are the O and the X of the class symbol, and then you're left with the responsibilities play, place symbol, display, accumulate, scores, quit, and reset. And so now that you have your consolidated classes and responsibilities, you now do the allocation, you do the mapping. So here's what I did. The class game was allocated the responsibilities play, accumulate scores, quit, and reset. The class board had display responsibilities. The class game grid has place symbol responsibilities. And then I find that the classes symbol, player, human, computer, and row have no responsibilities yet. So the question is, should we keep them? Should we discard them? We don't know. Okay? And we'll know later when we create all the scenarios and then walk those scenarios through the classes, and we'll identify more responsibilities, potentially more classes, but certainly more responsibilities that will ideally go to these other classes that we've identified that don't have any responsibilities today. And by the way, after we've gone through all the scenarios and we find that certain classes don't have responsibilities, well, we just throw them away. It's our design. So now we go through the next step, which is define scenarios and then use them to walk through the design you have so far. So let's create a scenario. This first scenario will be very general. We just want to get something, see if we, something that will broadly cover all the classes, see if we have the necessary classes, things like that. This scenario is really not that helpful in identifying fine-grained details about the classes, but it's a nice place to start, okay? So this is like a holistic global scenario that goes something like this. We'll start a new game. We'll decide and set who plays first, the human or the computer. The first player should get assigned the X as the symbol. The second player should get assigned the O. The first player should place his or its symbol, if it's the computer, at an empty location on the board. The second player should do likewise, and then this step should be repeated until one player has 3 of his or its symbols in a row, column, or diagonal, or there are no more squares to play. If a player managed to get all his symbols in a row, column, or diagonal, then he wins, or she wins, or the computer wins. And if all the squares get exhausted by the time and no player has won, the game is declared a draw. Once the game ends, the scores for the players have to be accumulated. The winning player gets 1 added to his or its score. No change is made to a losing player's score. Also, if both players' scores both players' scores stay the same, that is 0 is added if the game ends in a draw. Hey, if the user wishes, start a new game, else quit. Once again, note that this is a general scenario, and obviously if we want to do fine-grained design, then we've got to define more specific scenarios. And so now you do a scenario walkthrough. That is, you go through each step of the scenario that you designed, see the previous slide, and you go through each step and say, which class should handle this? Which class should handle the next step? Which class should handle this next responsibility? Okay. So you'll find that there is no class that responds when starting a new game. So now you need a new class. Let's create one. Let's call it game controller. Obviously, game controller and game will collaborate. Who's supposed to handle symbol creation and placement? I guess we'll let symbol handle the creation and board the placement. Should we have place symbol invoking play? Should we have? Does the game need need a function called check result. You'll find that board, game, grid, and game are collaborators, and so on. And so now we arrive at, after we've gone through enough scenarios, we arrive at a pretty complete design. Okay, so here are some of the classes that were actually there in the final program that got implemented. So this was a program that I implemented as an example of Android development. So this was my example in my mobile application class. So this was actually an implemented program, and here were the classes in it. So the first class was game. It represented a single tic-tac-toe game. Its responsibilities were play and check result. Its collaborators were game session, game view, and grid. Then I had game view, which represented the visual display of a tic-tac-toe game. Its responsibilities were to place the symbol and show scores, and it collaborated with game, which was the underlying representation of the game. Then I had game grid that represented the 3x3 tic-tac-toe grid. It also had a responsibility called place symbol, and it also provided a method called get empty squares for obvious reasons. And it collaborated with game. Then I had game session, which represented a tic-tac-toe playing session. It had a bunch of responsibilities such as starting a new game, play a new game, quit, decide who was whether player 1 was the computer, player 2 was the computer. It accumulated the scores like we thought it should, etc. And it collaborated with game and game view. And then finally, I had a class called symbol that represented a tic-tac-toe symbol, either an X or an O. It had no responsibilities, but it did collaborate, other than returning an X or an O. It collaborated with game. And then just to show you how far you can get just with responsibility-driven design, you can actually get down all the way down to the contracts, to the actual contracts for all the methods. And here is an example of those. So game had a method called play. Its parameters were grid, symbol, X and Y, which were the coordinates at which you placed you placed your X or the O. It had check result and set state. You had is active, is one, is drawn, and then game view had place symbol, which took as parameter symbol, an X and a Y, and returned success or failure, things like that. So you can go pretty far with object-oriented design without even writing a single line of code. And once you get down to this level where you have the objects, you have the classes, the methods, all the way down to their contracts, pretty much the design is complete. So what did we learn in this lecture? So like we said earlier when we presented the slide on learning outcomes, we expected students to studying this module to come away with being reminded of object-oriented concepts, things like class and type and method and virtual method and abstract class, things like that. So we covered those. We tried to explain the rationale behind object-oriented design, this notion of designing based on real-world concepts, and why this notion of designing actually made sense. And then the idea was to get you guys competent with one technique for object-oriented design known as responsibility-driven design. We walked you through all the steps in responsibility-driven design, identifying candidate classes, candidate responsibilities and collaborators, consolidating them, using scenarios as a way to validate all of this, and then ultimately coming up with a complete design. And finally, here are the references used in developing this lecture. It is chapter 13 from the hopefully now familiar Developing Object-Oriented Software book, pages from which are posted online, and then a paper titled Reflections on Object-Oriented Design and CRC Cards. This has also been posted online. And by the way, we've also posted the entire CSC 560 Lab 1 online, from which the example on walking through the O design checklist has been drawn.